Look up at the night sky. What do you see? A scattering of stars, maybe a planet or two, the faint glow of the Milky Way stretching across the darkness. But what if I told you that everything visible to the naked eye, every twinkling light, every cosmic landmark, is just the tiniest fraction of what's really out there? The universe is an endless tapestry of mysteries, and for all our telescopes, probes, and equations, we've barely begun to unravel its secrets. Even today, with technology that lets us peer billions of light years into the void, some phenomena defy explanation, leaving scientists scratching their heads. Strange signals from deep space, objects moving faster than physics allows, even gaps in our understanding of reality itself. These are the enigmas that remind us how much we still have to learn. That's why we're diving into 25 of the most baffling, awe-inspiring mysteries the cosmos has to offer. From rogue planets drifting between galaxies to eerie radio bursts that seem to whisper from the edge of existence, these aren't just curiosities, they're the frontiers of human knowledge. Think about it, every time we've unraveled one cosmic riddle, it's led to even bigger questions, like peeling back layers of an infinite onion. And here's the thrilling part, some of these phenomena might hold the keys to understanding the very fabric of the universe, from dark matter's invisible grip to the possibility of dimensions beyond our own. So if you've ever stared at the stars and wondered what's really going on out there, you're in the right place. This isn't just a list, it's a journey to the edges of science, where the rules we take for granted start to bend and break. By the end, you'll see the cosmos not as a static backdrop, but as a living, breathing puzzle, one we're only beginning to solve, ready to have your mind blown. Let's begin. Imagine something out there in the cosmos so powerful that entire galaxies, including our own Milky Way, are being dragged toward it at incredible speeds. That's exactly what scientists stumbled upon when they discovered the Great Attractor, a gravitational behemoth lurking about 250 million light-years away, hidden behind the thick dust and stars of our galaxy's own plane. At first, astronomers noticed something odd. Galaxies in our local cluster weren't just drifting apart as the universe expanded. They were all streaming toward a single, unseen point in space, like leaves caught in a cosmic river current. The sheer scale of this mystery is staggering. The Great Attractor's gravitational pull suggests it has the mass of tens of thousands of Milky Ways packed into a region of space just a few 100 million light-years across. But here's the catch, we can't see it directly. Our view is blocked by what astronomers call the zone of avoidance, a stretch of the Milky Way's dense dust and gas that obscures nearly 20% of the night sky from our perspective. It's like trying to spot a lighthouse through a thick fog while standing in the middle of a bustling city. So what could it be? Some theories suggest it's an immense concentration of dark matter, the invisible scaffolding of the universe that binds galaxies together. Others propose it might be a supercluster of galaxies so densely packed that their combined gravity creates this colossal tug. But even these explanations fall short. Recent observations hint that the Great Attractor itself might be just a small part of an even larger structure, a mind-boggling web of galaxies and dark matter known as Laniakea, our home supercluster. The deeper we look, the more questions arise. Why does the Great Attractor's gravitational influence extend so far? What unseen forces are at play? Every answer peels back another layer, revealing just how much we still don't understand about the universe's hidden architecture. One thing's certain, this cosmic mystery reminds us that even the biggest structures in the universe can remain invisible, shaping the fate of galaxies while lurking in plain sight, or rather just out of it. Now picture this, an invisible force holding the universe together, its presence felt everywhere but never seen. That's dark matter, the cosmic ghost that makes up roughly 85% of all matter in the universe, yet refuses to show itself. We know it's there because of its gravitational fingerprints, galaxies spinning faster than they should, cosmic structures forming on scales that visible matter alone could never explain. Without dark matter, the universe as we know it would fly apart, yet after decades of searching, we still haven't caught a single glimpse of it. Take spiral galaxies, for example. Stars on the outer edges should orbit more slowly than those near the center, just like planets farther from the sun move at a more leisurely pace. But when astronomers measured these rotations, they found something bizarre. The outer stars were whipping around just as fast as the inner ones. The only explanation, an enormous halo of invisible matter, wrapping around each galaxy like an unseen hand, providing the extra gravity needed to keep everything from flinging into the void. Then there's the cosmic web, the vast scaffolding of galaxies stretching across the universe. Computer simulations show that without dark matter's gravitational pull, ordinary matter would never have clumped together into galaxies and clusters. Instead, it would have remained a thin, featureless soup. Dark matter acted as the universe's blueprint, guiding everything into place. Yet for all its influence, it interacts with light and ordinary matter so weakly that even our most sensitive detectors come up empty. So what is it made of? Theories range from weakly interacting massive particles to actions, hypothetical particles so light they barely register. Some experiments hunt for dark matter deep underground, shielded from cosmic noise, while others try to create it in particle colliders. But so far, every search has turned up nothing. Even stranger, dark matter might not be one thing at all. It could be an entire shadow universe of particles, each as mysterious as the last. The more we learn, the more questions arise. Why does dark matter cluster in halos around galaxies? Could it interact with itself in ways we haven't imagined? Every dead end in the search only deepens the mystery, reminding us that the bulk of the universe is still hidden in plain sight. Until we crack this cosmic code, dark matter remains one of the greatest unsolved puzzles in science, a silent architect shaping everything we see, yet forever out of reach. If dark matter is the invisible glue holding galaxies together, dark energy is the mysterious force tearing the universe apart, an anti-gravity pushing everything into an accelerating expansion that defies all expectations. Picture a balloon inflating faster and faster, not because you're blowing more air into it, but because the rubber itself is changing its properties, stretching space-time from within. That's the enigma scientists faced in the late 1990s when two teams of astronomers made a Nobel Prize-winning discovery. Distant supernovae were dimmer than they should have been, meaning the universe wasn't just expanding, it was speeding up. This revelation flipped cosmology on its head. Einstein's cosmological constant, a mathematical fudge he once called his greatest blunder, suddenly became the leading explanation. Think of it as an inherent energy woven into the fabric of space itself, a constant pressure that doesn't dilute as the universe grows. But here's the catch: quantum physics predicts this energy should be 120 orders of magnitude stronger than what we observe. That's like calculating the weight of a mountain and finding it weighs less than a feather. The mismatch is so colossal that some researchers wonder if we're missing something fundamental about how gravity works. Alternative theories abound. Maybe dark energy isn't constant at all. Perhaps it's a dynamic field called quintessence, evolving over time like an invisible fifth force. Or maybe Einstein's theory of relativity breaks down on cosmic scales, requiring a radical rewrite of physics. Then there's the chilling possibility that we're seeing the first hints of a big rip, where dark energy grows so dominant it shreds galaxies, stars, and even atoms in the far future. What makes dark energy so unsettling is its timing. For billions of years, gravity had the upper hand, pulling matter into galaxies and clusters. Then, around 5 billion years ago, dark energy took over like a switch flipping in the cosmic dark. Why then? Was it random, or does it hint at some deeper law we haven't uncovered? Every telescope, from Hubble to the upcoming Nancy Grace Roman Space Telescope, is hunting for clues, mapping the universe's expansion in unprecedented detail. One thing's certain, dark energy isn't just another puzzle, it's a glaring hole in our understanding of reality. Whether it's a misunderstood constant, a new force, or a sign our physics is incomplete, its resolution could redefine the universe's ultimate fate. For now, it remains the most dominant yet least understood ingredient in the cosmic recipe, silently dictating everything while leaving no trace of its true nature. Somewhere in the vast darkness of space, a cosmic flashbulb goes off, blasting out more energy in a millisecond than our sun emits in 3 days. Then, just as suddenly as it appeared, it's gone. These are fast radio bursts, or FRB, some of the most explosive and enigmatic signals ever detected. First discovered in 2007, these ultra-brief radio pulses arrive from galaxies billions of light-years away, flickering like celestial Morse code with no obvious pattern. But the real twist: most vanish without a trace, while a rare handful repeat, sending multiple bursts from the same patch of sky, deepening the mystery of what could possibly power such violent, fleeting eruptions. Take FRB 2001-2020, for example. Nestled in a dwarf galaxy 3 billion light-years distant, this repeater has been firing off signals since its discovery, sometimes in frantic clusters, other times falling silent for months. Then there's FRB 2019-04, which erupted with a staggering 16 bursts in just 1 hour. The unpredictability has astronomers scrambling. Imagine trying to study a fireworks display where most explosions happen once, but a few launchers sporadically fire again, with no schedule, no warning, and no identifiable trigger. So what's behind these cosmic lightning strikes? One leading suspect is magnetars, super-dense, highly magnetized neutron stars that spin like cosmic tops, their intense magnetic fields occasionally snapping like rubber bands, releasing titanic bursts of energy. In 2020, astronomers caught a magnetar in our own galaxy emitting an FRB-like pulse, adding weight to the theory. But here's the catch: some FRBs release energy levels far beyond what even magnetars should theoretically produce. Could they be collisions between neutron stars or black holes, the aftermath of a star being shredded by a supermassive black hole? Or, as some have daringly speculated, might they be artificial alien beacons or propulsion signatures? The repeating FRBs complicate things further. If most bursts are one-off cosmic accidents, why do a few sources keep flashing? One tantalizing clue lies in their environments. Many repeaters trace back to turbulent regions of star formation, where extreme celestial objects jostle like commuters in a crowded subway. Others appear near the edges of their host galaxies, suggesting they might be hurled there by gravitational interactions. Each location hints at different formation stories. No single explanation fits all. What makes FRBs so captivating isn't just their mystery, but their potential as cosmic tools. As these bursts traverse the universe, they interact with the sparse matter between galaxies, carrying encrypted clues about the universe's structure. Some researchers even propose using them to map the elusive, missing matter, ordinary atoms that should exist but haven't been accounted for. Yet every discovery seems to birth new questions. Why do some FRBs show bizarre polarization patterns, as if their signals have been twisted by powerful magnetic fields? Could there be entirely new classes of FRBs we haven't recognized yet? For now, these millisecond enigmas remind us how much of the universe operates in extremes: brief, violent, and utterly unpredictable. Whether they're the death cries of exotic stars or something far stranger, one thing's clear: in the hunt to understand FRBs, we're not just decoding cosmic static. We're listening to the universe's most fleeting whispers, each one a riddle wrapped in a pulse of radio light. On the night of August 15, 1977, a radio telescope in Ohio picked up something extraordinary: a 72-second burst of radio waves so strong that the astronomer monitoring the data scribbled, "Wow," in the margin of the printout, giving the signal its iconic name. Detected by the Big Ear telescope as part of the search for extraterrestrial intelligence, or SETI, this narrowband transmission seemed to scream artificial from the moment it was found. Unlike the static hiss of cosmic background noise or the erratic pulses of natural radio sources, the WOW signal had all the hallmarks of something deliberate, a focused frequency matching the hydrogen line, a logical choice for any civilization trying to announce its presence across the interstellar void. The signal's intensity spiked and faded exactly as expected if it came from deep space, rising and falling as Earth rotation swept the telescope's beam across its origin point in the constellation Sagittarius. But here's where the mystery deepens. Despite decades of follow-up scans using instruments far more sensitive than Big Ear, the signal never repeated. Not once. It's as if the universe flicked a cosmic flashlight at us and then vanished without a trace. So what could it have been? The leading natural explanation points to hydrogen clouds or comets, but neither fits neatly. The frequency was too clean, too precise, and comets weren't in the right position at the time. Others suggest it might have been a reflected human transmission, a rogue radio signal bouncing off space debris, but no known broadcasts matched its profile. Then there's the tantalizing, spine-tingling possibility. Was it a fleeting hello from another civilization, a beacon switched on just long enough to tease us before disappearing into the cosmic noise? The WOW signal's legacy isn't just about what we heard, it's about what we didn't. Its silence since that night forces us to confront the needle in a haystack challenge of SETI. Space is vast, time is long, and even if other civilizations are out there shouting, their signals might be as brief and random as a lightning strike. Yet that single wow remains a ghost in the machine, a whisper from the dark that reminds us, sometimes the most profound mysteries aren't the ones we solve, but the ones that leave us staring at the stars, wondering if we were ever meant to hear them at all. In the constellation Cygnus, about 1,500 light-years from Earth, a star behaves like nothing else in the known universe. KIC 8462852, better known as Tabby's star after astronomer Tabetha Boyajian, who first documented its bizarre flickering, doesn't play by the rules. Most stars dim in predictable, rhythmic patterns caused by orbiting planets or internal cycles, but Tabby's star drops in brightness erratically, sometimes by as much as 22%, as if something massive and irregular is passing in front of it. These dips last for days or weeks with no discernible pattern, leaving astronomers scrambling for explanations that range from the plausible to the downright fantastical. Initially, the leading theory pointed to a swarm of comets, thousands of them, with tails so thick they'd block starlight in chaotic, unpredictable ways. But comets couldn't explain the star's long-term dimming. Between 1890 and 1989, archival data showed Tabby's star had faded by a staggering 14%, a decline orders of magnitude beyond what any known natural phenomenon could produce. Stars don't just dim like that without a reason. That's when things got weird. Some researchers floated the idea of alien megastructures, specifically a Dyson swarm, a hypothetical array of energy-collecting satellites built by an advanced civilization. The concept, first proposed by physicist Freeman Dyson in the 1960s, suggests a society could harness a star's power by encircling it with orbiting solar panels or habitats. While the math showed such structures could account for the irregular dimming, the scientific community remained skeptical. After all, extraordinary claims require extraordinary evidence, and no one was ready to declare the discovery of aliens based on light patterns alone. More grounded theories emerged. Perhaps the star had recently devoured a planet, sending debris spiraling into a chaotic dust cloud. Or maybe it was surrounded by a warped, uneven ring system like Saturn's but on a stellar scale. Then there's the possibility of intervening material, some dense patch of interstellar dust drifting between us and the star, though why it wouldn't affect neighboring stars remains unclear. The truth is, every explanation so far has holes. Even the latest studies, which suggest finely crushed dust particles might be responsible, can't fully replicate Tabby's star's extreme behavior. It's become a cosmic Rorschach test. What you see in its dips often says as much about your assumptions as it does about the star itself. Perhaps the most tantalizing aspect of this mystery is what it reveals about how we explore the unknown. When faced with something unprecedented, science often cycles through the familiar before embracing the extraordinary. Tabby's star forces us to question not just what's out there, but how we interpret the universe's quirks when our textbooks fall short. Whether it's comets, dust, or something beyond our current understanding, one thing's certain: this star isn't done keeping us guessing. The universe is unimaginably vast, with hundreds of billions of galaxies, each home to hundreds of billions of stars. Statistically, the numbers scream that we shouldn't be alone. Even if life is extraordinarily rare, the sheer scale of existence suggests Earth should be just one among countless inhabited worlds. So where is everyone? This is the Fermi Paradox, the glaring contradiction between the high probability of extraterrestrial civilizations and our total lack of evidence for them. Named after physicist Enrico Fermi, who famously asked, "But where are they?" during a casual lunchtime conversation, this paradox has haunted scientists for decades. One unsettling explanation is the Great Filter, a hypothetical barrier that prevents life from progressing to advanced stages. The filter could lie in our past, meaning the leap from non-living chemistry to complex life is so improbable we're among the rare exceptions. Or worse, it might await us in the future. Perhaps every civilization reaches a point where it inevitably destroys itself, through climate collapse, nuclear war, or unchecked artificial intelligence. If true, the eerie silence of the cosmos isn't a mystery, it's a graveyard. Then there's the zoo hypothesis, the idea that advanced civilizations deliberately avoid contact, observing us like animals in a cosmic nature preserve. It's a chilling thought that we might be quarantined, deemed too primitive or too dangerous to engage with. Alternatively, they could be signaling in ways we don't yet recognize. Imagine ants at the base of a radio tower, oblivious to the messages crackling above them. Our technology, advanced as it seems to us, might be primitive compared to the communication methods of older civilizations. Time scales add another layer of strangeness. The universe is 13.8 billion years old, but hominids have only walked Earth for a few million years, a blink in cosmic terms. Intelligent civilizations could have risen and fallen long before Earth even formed. Their signals faded into the background hum of the universe. Or perhaps they're here already, hidden in plain sight, their technology indistinguishable from natural phenomena. The paradox forces us to confront uncomfortable possibilities. Are we the first, the last, or is the truth something we haven't even imagined yet? Every silent radio telescope, every empty exoplanet survey deepens the mystery. Until we find proof otherwise, the Fermi Paradox remains a haunting question mark, not just about alien life, but about our own place in the cosmos. The universe, we've been told, has no preferred direction, no up, no down, no cosmic landmarks to give one region an edge over another. This assumption, known as the cosmological principle, is the bedrock of modern astronomy, the idea that on large scales, matter and energy are spread evenly in all directions. But what if the universe is playing favorites? That's the unsettling question raised by a bizarre anomaly in the cosmic microwave background, or CMB, the afterglow of the Big Bang itself. Dubbed the axis of evil by skeptics, this pattern of unexpected alignments in the CMB's temperature fluctuations suggests something deeply strange. The universe might have a preferred axis, a cosmic tilt that defies everything we thought we knew. First detected by NASA's Wilkinson Microwave Anisotropy probe in the early 2000s, the anomaly appears as a peculiar alignment of hot and cold spots in the CMB, stretching across the sky like an invisible spine. These spots aren't randomly distributed as they should be. Instead, they seem to line up along a specific plane, pointing toward the constellations Leo and Aquarius with eerie precision. Even stranger, this axis roughly aligns with our solar system's ecliptic plane, the path Earth takes around the Sun. At first, scientists dismissed it as a fluke, an artifact of measurement errors or foreground interference. But as more sensitive instruments like the Planck satellite confirmed the pattern, the discomfort grew. The odds of this happening by chance, less than 1 in 1,000. The implications are staggering. If the universe has a preferred direction, it undermines the cosmological principle, the idea that no observer holds a special place in the cosmos. It's like discovering that all the scattered paint splatters on a canvas secretly point to one hidden corner. Some theories scramble to explain it. Could it be the gravitational tug of unseen structures beyond our observable universe pulling space-time like a sheet? Or is it evidence of a pre-Big Bang universe, a relic imprint of something older than time itself? Then there's the more unsettling possibility. What if it's not the universe that's tilted, but our understanding of it? Critics argue the axis of evil might be a mirage, a trick of perspective caused by incomplete data or overlooked systematic errors. After all, the CMB is faint, and Earth's motion through space creates its own subtle distortions. But even after accounting for these factors, the signal persists, gnawing at the edges of cosmology like a stubborn splinter. The name Axis of Evil isn't just dramatic flair, it reflects how deeply this anomaly threatens foundational science. Accepting it would mean rewriting textbooks, abandoning cherished assumptions about the universe's symmetry. Yet for all the controversy, the Axis of Evil does something remarkable. It reminds us that the universe owes us no answers. Every time we think we've mapped the cosmic rulebook, it throws us a curveball, daring us to look deeper. Whether this alignment is a quirk of physics or a sign of something profoundly new, one thing's clear: the cosmos still has secrets, and they're written in the oldest light there is. Picture two coins flipped simultaneously on opposite sides of the universe, yet no matter how far apart they are, they always land matching heads or tails in perfect sync. That's the essence of quantum entanglement, a phenomenon so bizarre Einstein famously dismissed it as spooky action at a distance. At the subatomic level, particles like electrons or photons can become inextricably linked, sharing a single quantum state. Change one, say, by measuring its spin, and its entangled partner instantly mirrors that change, even if it's light years away. This isn't theoretical. Lab experiments have confirmed it repeatedly, leaving physicists grappling with a reality that seems to defy the cosmic speed limit, light itself. Here's where relativity clashes with quantum weirdness. Einstein's theory insists nothing can travel faster than light, yet entanglement appears to transmit information instantaneously. Imagine throwing a switch in Tokyo and a light flashing in New York with zero delay, no signal, no carrier, just an inexplicable immediate connection. The key lies in what's actually being sent. While the particle states correlate, no usable data travels between them. It's like opening a letter in Paris and knowing its twin in Sydney must also be open without any way to control what's written inside. This subtle distinction keeps relativity intact but forces us to redefine what we mean by connection. The implications are staggering. If harnessed, entanglement could revolutionize communication. Quantum encryption already exploits this phenomenon, creating unbreakable codes where any eavesdropping attempt instantly alerts the sender, like a sealed letter that self-destructs if someone peeks. China's Misha satellite demonstrated this in 2017, beaming entangled photons to ground stations over 700 miles apart. But the real dream? Quantum networks linking cities or even planets, where information hops between entangled nodes faster than traditional signals could crawl through cables or radio waves. Yet the challenges are as immense as the promise. Entangled states are fragile, shattered by the slightest interference, a photon colliding with a dust particle, a stray magnetic field. Maintaining coherence over long distances demands near-perfect isolation, like trying to whisper a secret across a hurricane. Some propose quantum repeaters, devices that extend entanglement's reach by stitching shorter links together, but even these are in their infancy. What makes entanglement truly mind-bending is its philosophical weight. It suggests that at the deepest level, the universe isn't made of separate, isolated objects, but a web of relationships where distance is an illusion. Whether this hints at hidden dimensions, a holographic cosmos, or something beyond our current physics, one thing's clear: entanglement isn't just a lab curiosity. It's a glimpse into the universe's most intimate wiring, a reminder that reality, at its core, is far stranger than fiction. In the vast emptiness of space, where precision is everything, and even the smallest deviations can rewrite our understanding of physics, two tiny spacecraft gave scientists a headache they couldn't shake. The Pioneer 10 and 11 probes, launched in the early 1970s to explore the outer solar system, were expected to coast toward the stars with predictable trajectories. But as they ventured farther from the sun, something strange happened. Both probes began slowing down ever so slightly, as if an invisible hand were gently tugging them backward. This minuscule deceleration, just a fraction of a nanometer per second squared, became known as the Pioneer Anomaly, a cosmic puzzle that defied explanation for decades. At first, mission scientists dismissed it as a glitch, perhaps a software error or residual fuel leakage. But the anomaly persisted, meticulously tracked by the spacecraft's radio signals as they drifted deeper into the void. By the late 1990s, the drift was undeniable. Pioneer 10, already billions of miles from Earth, was over 240,000 miles off course from where Newton's laws predicted it should be. That's like throwing a paper airplane across a room only to watch it veer inexplicably sideways before hitting the floor. The hunt for answers began in earnest. Could it be the faint push of thermal radiation? The probe's plutonium-powered generators emitted heat, and even the tiniest unevenness in that emission might create a recoil effect. Computer models suggested this could explain part of the anomaly, but not all of it. Others proposed more exotic theories. Maybe gravity itself behaved differently at extreme distances, weakening less than expected. Some even speculated about unseen dark matter clumps or subtle flaws in Einstein's theory of relativity. Then, in 2012, a breakthrough emerged. A painstaking analysis of old telemetry data, combined with new thermal modeling, revealed that heat radiation from the probe's power systems wasn't just a factor, it was likely the primary culprit. The way heat radiated unevenly from the spacecraft surfaces created just enough recoil to account for the anomaly. Case closed, not quite. Even after accounting for thermal effects, a whisper of the anomaly remained, a discrepancy too small to dismiss entirely but too faint to confirm. The Pioneer Anomaly's legacy lingers because it exposes how much we still don't know about the subtle forces at play in deep space. It's a reminder that even our most trusted equations might hide gaps, and that the universe loves throwing curveballs, especially when we think we've got it all figured out. Whether residual mystery or measurement quirk, those drifting probes taught us one invaluable lesson. In the cosmic dance of gravity and motion, there's always room for surprises. High above Earth, lost in the endless swirl of satellites and space junk, one object has sparked more wild speculation than any other: the so-called Black Knight satellite. Stories claim this mysterious craft has been orbiting our planet for 13,000 years, an extraterrestrial artifact watching us from the shadows. Some even say Nikola Tesla intercepted its signals in the 1890s, picking up strange radio pulses he couldn't explain. But peel back the layers of myth, and the truth becomes far more fascinating than fiction. The Black Knight legend began in 1954, when newspapers reported that the U.S. Air Force had detected two mysterious satellites orbiting Earth, impossible at the time, since no nation had yet launched one. Decades later, blurry NASA photos from the 1990s seem to show a dark, irregular shape floating near the space shuttle, fueling theories of an alien probe. The myth snowballed, blending with misinterpreted thermal blanket debris sightings and even a mislabeled photo of a lost astronaut's glove. Reality, as it turns out, is far less cinematic but no less intriguing. The satellite detected in the 1950s, almost certainly a misidentified meteor or radar echo, amplified by Cold War paranoia, the famous NASA images. Likely just a dropped piece of equipment or insulation, ordinary debris caught in the harsh light of space. The truth is, Earth's orbit is cluttered with over 100 million fragments of defunct satellites, spent rocket stages, and other remnants of our spacefaring era. Some tumble erratically for years before burning up, their twisted shapes easily mistaken for something more sinister under the right lighting. So why does the Black Knight myth endure? Part of it taps into our deep fascination with the unknown, the idea that we're not alone and that evidence might be hiding just out of sight. But it also reflects a grain of truth. Space is vast and not everything up there is accounted for. Even today, the U.S. Space Surveillance Network tracks over 27,000 objects larger than a softball, with countless smaller pieces slipping through the cracks. Every so often, a new mystery satellite emerges, only to be identified as a forgotten booster stage or a stray bolt from some decades-old mission. What makes the Black Knight special isn't its reality, but its symbolism. In an age where satellites are mundane, it represents that last whisper of cosmic mystery, a reminder that even in our own backyard, the line between myth and reality can blur. After all, if an alien artifact were orbiting Earth, wouldn't it look exactly like just another piece of space junk, at least until it decided otherwise? Physics has a way of humbling even the brightest minds, like when an engine that shouldn't work seems to. Enter the MDrive, or electromagnetic drive, a propulsion concept so baffling it's been called the impossible engine. Proposed in the early 2000s by British engineer Roger Scheuer, the MDrive promised something revolutionary: thrust without fuel. No rockets, no propellant, just microwaves bouncing around in a closed chamber generating a whisper of forward motion. It defied Newton's third law, the one that says every action must have an equal and opposite reaction. Without expelling mass, how could it push anything? Yet when NASA Eagleworks lab tested it in 2016, their rig detected a tiny but measurable thrust. The scientific equivalent of a gasp rippled through the community. Were the laws of physics about to be rewritten, the allure was undeniable. Imagine spacecraft gliding between planets without lugging tons of fuel, or probes reaching Alpha Centauri within human lifetimes. The MDrive flirted with that dream, offering a way to dodge the tyranny of the rocket equation, the brutal math that makes space travel so heavy and expensive. But excitement quickly collided with skepticism. Peer-reviewed studies failed to replicate the results consistently. Some teams found hints of thrust, others detected nothing but experimental noise. The force measured was so minuscule, often just a few micronewtons, barely enough to budge a grain of sand, that critics argued it could easily be explained by thermal expansion, magnetic interference, or even the subtle push of heat radiating off the device. Then came the kicker. In 2021, a team at Dresden University built an ultra-sensitive test rig inside a vacuum chamber, meticulously accounting for every possible external influence. Their verdict: the thrust vanished. What earlier experiments might have seen as a breakthrough now looked like measurement error. Yet, like a cosmic whodunit, the story didn't end there. MDrive believers pointed out flaws in the Dresden setup, while skeptics doubled down, insisting the burden of proof lay with those claiming to overturn centuries of physics. What makes the MDrive so compelling isn't just the technical debate, it's the philosophical rift it exposes. Science thrives on falsifiability, the idea that a hypothesis must be testable and disprovable. But when experiments disagree, how do we know which side is right? The MDrive forces us to confront the messy frontier of discovery, where hope and rigor wage a quiet war. For now, the engine remains in limbo, not quite debunked but far from confirmed, and that's where the real lesson lies. Sometimes, the universe's most tantalizing mysteries aren't about finding answers, but learning how carefully we must question them. Imagine a bubble in the universe so vast that if you stood at its center, the nearest galaxy would be millions of light-years away, an emptiness so profound it challenges our understanding of cosmic structure. This is the Boötes Void, a spherical region of space spanning 330 million light-years, where galaxies are almost entirely absent. To put that in perspective, our Milky Way has dozens of galactic neighbors within just a few million light-years. But in the Boötes Void, you could travel the equivalent of a quarter of the observable universe and encounter fewer than 60 galaxies, a cosmic desert on a scale that stuns astronomers. Discovered in the 1980s during surveys of galactic distribution, the void immediately stood out as an anomaly. Large-scale structure models predict that matter should clump into filaments and clusters, with voids in between, but none as extreme as this. It's like expecting a sponge with small air pockets and finding instead a gaping hole the size of the sponge itself. The standard explanation, that such voids form from regions of slightly lower density in the early universe, doesn't quite fit. Simulations struggle to produce anything so empty without tweaking the rules of cosmology. One theory suggests the Boötes Void might be the product of multiple smaller voids merging over billions of years, like soap bubbles colliding to form one colossal cavity. Others speculate it could be evidence of an encounter with a parallel universe, a wild idea that hinges on unproven multiverse theories, but the most unsettling possibility. That we're seeing the imprint of something even more exotic, a defect in the fabric of spacetime itself, left over from the universe's violent birth. What makes the void particularly eerie is its isolation. The few galaxies within it aren't just scarce, they're oddly distributed, as if clinging to the edges of some invisible boundary. Some show strange star formation patterns, their gas reservoirs depleted by the void's relentless emptiness. It's a stark reminder that galaxies aren't just islands in space, they're products of their environment, shaped by forces we're only beginning to map. The Boötes Void forces us to ask, is this a fluke or a sign that our models miss something fundamental? Either way, it stands as a humbling reminder the universe reserves the right to surprise us, carving out mysteries in the places we least expect. The Moon has a secret hidden in its rocks, a ghostly echo of a magnetic field that shouldn't exist. Today, our lunar neighbor is a quiet, airless world with barely a whisper of magnetism, but billions of years ago, it may have crackled with its own magnetic shield, rivaling Earth's in strength. This revelation comes from ancient lunar samples brought back by Apollo astronauts, their metallic grains frozen in time like microscopic compasses pointing to a forgotten chapter of the Moon's past. How could something so small and geologically stagnant have ever generated such a powerful field? The answer might rewrite what we know about planetary dynamos. For decades, scientists assumed the Moon's core was too small and sluggish to sustain a magnetic dynamo, the churning flow of molten metal that powers Earth's magnetic field. Without plate tectonics or significant heat sources, the Moon seemed destined to be magnetically inert. But then came the rocks. Analysis of Apollo-era basalts revealed something astonishing. Some samples bore traces of magnetization so strong they suggested a field intensity up to 100 times greater than the Moon's current feeble magnetism. It's like finding a fossilized lightning bolt in a desert proof of a tempest where we expected only calm. The leading theory points to an early lunar core supercharged by violent cosmic events. Shortly after the moon's formation, its core may have been hot enough to churn vigorously, driven by the lingering heat of its creation and the gravitational tug of war with Earth. Some models suggest that as the moon cooled, its mantle may have acted like a thermal blanket, trapping heat and keeping the core simmering far longer than expected. Others propose that massive asteroid impacts billions of years ago could have jolted the core into temporary dynamo action, like stirring a dying ember to life. But the plot thickens. Recent studies of younger lunar rocks, some as recent as 1 billion years old, hint that the moon's magnetism didn't fade smoothly. Instead, it flickered on and off like a sputtering candle, suggesting multiple dynamo mechanisms at play. One tantalizing idea involves a phenomenon called core crystallization. As the moon's inner core slowly solidified, the release of latent heat and light elements could have reignited convection in the remaining molten outer core. It's a delicate dance between cooling and reheating, one that might explain why the moon's magnetic personality was so erratic. The implications stretch far beyond lunar geology. If something as small as the moon could sustain a dynamo, it raises questions about other rocky worlds, Mercury, Mars, even distant exoplanets. Maybe magnetism isn't the exclusive domain of large, active planets. Maybe it's a fleeting phase some worlds pass through, their cores whispering secrets before falling silent. For now, the moon keeps its magnetic past locked in those silent rocks, a puzzle waiting for the next generation of lunar explorers to decode, one grain, one sample, one revelation at a time. When astronomers first spotted Oumuamua tumbling through our solar system in October 2017, they knew immediately it was something extraordinary, not just another asteroid or comet, but the first confirmed visitor from interstellar space. Its name, Hawaiian for scout or messenger, captured the sense of wonder it inspired, but the real shock came as researchers studied its trajectory. Instead of slowing down as expected under the sun's gravity, this peculiar object sped up slightly, as if propelled by an unseen force. No outgassing the telltale jets of gas that give comets their boost was detected. No tail, no coma, nothing but the object itself, gliding through space with a nudge physics couldn't easily explain. Then there was its shape. Observations suggested Oumuamua wasn't spherical or even vaguely potato-like like most space rocks. It appeared unusually elongated, perhaps 10 times longer than it was wide, resembling a cosmic pancake or cigar tumbling end over end. Such extreme proportions are rare in nature, where objects tend toward lumpy roundness under their own gravity. Even stranger, its brightness fluctuated wildly as it rotated, suggesting an uneven, possibly metallic surface reflecting sunlight in unpredictable bursts. Theories erupted like supernova. Could it be a fractal like dust iceberg, a fragile aggregate of interstellar material held together by weak forces? Some scientists pointed to nitrogen ice, noting that as it sublimated, it might provide just enough thrust to match the observed acceleration without visible outgassing. Others proposed it was a shard ripped from a Pluto-like exoplanet, explaining both its composition and odd shape. But the most provocative idea came from Harvard astronomer Avi Loeb, who suggested Oumuamua might be artificial, a relic of alien technology, perhaps a light sail or derelict probe. His reasoning hinged on the object's unusual reflectivity and acceleration profile, which resembled a thin, pushed object more than a natural body. The scientific pushback was swift and fierce, with critics arguing that extraordinary claims require extraordinary evidence, and Oumuamua's oddities, while puzzling, didn't rise to that level. The debate crystallizes a fundamental tension in astronomy. When does an anomaly become evidence of something beyond known physics? Oumuamua's fleeting visit, it's now beyond Neptune, never to return, left more questions than answers. Was it a bizarre but natural interloper or something more? The truth may lie in future detections. Upcoming telescopes like the Vera Rubin Observatory could spot dozens more interstellar objects, giving us a statistical sample to test these wild ideas. Until then, Oumuamua remains a tantalizing enigma, a cosmic passerby that challenged our assumptions, then vanished into the dark. Most cosmic nebulae swirl like spilled watercolor across the darkness of space, amorphous, flowing, chaotic. But in the constellation Monoceros, 2,300 light-years from Earth, there's an exception that defies the rules, the Red Rectangle Nebula. This striking structure looks less like a cloud of gas and more like a meticulously drafted architectural blueprint, its sharp geometric lines and nested X-shape glowing with an eerie crimson hue. At its heart, two aging stars dance in a tight orbit, their gravitational waltz sculpting the nebula's bizarre symmetry. Yet even with this clue, astronomers are still piecing together how such precise angles emerged from the usual celestial chaos. The secret lies in the central binary system, HD 44179. As one star evolved into a red giant, it began shedding its outer layers, while its smaller companion star funneled this expelled material into two cone-shaped outflows. Picture spinning a garden hose overhead. The water sprays in a double helix pattern. Now replace the hose with a dying star and the water with dust-laced gas, and you've got the basic recipe. But here's where things get weird. Instead of forming a typical hourglass shape, the cones overlap almost perfectly edge-on from our vantage point, creating the illusion of a glowing red rectangle. The sharp edges, that's likely thanks to dense rings of dust acting like stencils that carve the outflow into razor-straight lines. It's a cosmic art project where gravity, perspective, and physics collide. What makes the red rectangle truly puzzling isn't just its shape, it's the chemistry painting it crimson. Most red nebulae owe their color to hydrogen, but spectroscopy reveals something far stranger here. Complex organic molecules called polycyclic aromatic hydrocarbons, or PAH. These carbon-rich compounds, also found in coal and soot on Earth, fluoresce under starlight, giving the nebula its distinctive glow. Some scientists speculate these molecules could be precursors to life's building blocks, hinting that even in this geometric oddity, the ingredients for biology might be brewing. Yet mysteries linger. Why hasn't the nebula dissipated into a more diffuse structure over time? How did the dust rings form with such mathematical precision? And why do some observations suggest the rectangle isn't static, but pulsing with subtle luminosity changes? The nebula's central stars are destined to collapse into white dwarfs, their light fading, but for now, the red rectangle stands as a testament to the universe's flair for turning stellar death into geometry. It's a reminder that even in the cold vastness of space, there's room for the unexpected, the asymmetrical, and the strangely beautiful. If you think the Boötes void is vast, prepare to have your sense of scale shattered. Stretching an almost incomprehensible 10 billion light-years across, roughly 1/10 the observable universe, the Hercules Corona Borealis Great Wall isn't just a cosmic structure. It's a challenge to everything we thought we knew about how matter organizes itself in space. Discovered in 2013 by mapping gamma-ray bursts, this gargantuan filament of galaxies and galaxy clusters defies the very principles that govern cosmological models. According to our best understanding, there should be an upper limit to how big things can get in the universe, a theoretical cutoff point where density variations smooth out over extreme distances. Yet here we are, staring at a structure so colossal it makes superclusters look like specks of dust. The discovery hinged on a clever workaround. Because the wall lies so far away, its light taking up to 10 billion years to reach us, direct observation of its galaxies is nearly impossible. Instead, astronomers turn to gamma-ray bursts, the universe's most violent explosions, as cosmic breadcrumbs. These brief, intense flashes often mark the deaths of massive stars, and their distribution revealed an eerie pattern, an unusually dense band cutting across the constellations Hercules and Corona Borealis. Tracing the bursts was like seeing the outline of a mountain range in the dark, sketched only by distant lightning strikes. The implications were staggering. If real, this wall would surpass even the Sloan Great Wall, previously the record holder for largest known structure by a factor of 5. So why does this break the rules? Cosmology's foundational principle, the cosmological principle, states that at sufficiently large scales, the universe should appear roughly uniform, no dramatic lumps or gaps. Current models peg that scale at around 1.2 billion light-years. Beyond that, matter distribution should smooth out like cream stirred into coffee. The Hercules Corona Borealis Great Wall laughs at that assumption. Its existence suggests either our models are missing a crucial ingredient, perhaps exotic dark energy behavior or primordial quantum fluctuations, or we've stumbled onto evidence that the universe isn't as homogeneous as we believed. Some theorists even flirt with the idea of a pre-Big Bang imprint, a relic structure from an earlier cosmic cycle frozen into the fabric of space-time. Then there's the puzzle of its survival. Over such mind-bending distances, the expansion of space should have torn any coherent structure apart long ago. Gravity alone can't explain how something this vast held together across 10 billion years of cosmic evolution. One radical proposal suggests the wall might be a baryon acoustic oscillation, a frozen ripple from the early universe's sound waves stretched to impossible proportions by unknown physics. Others wonder if we're seeing a statistical fluke, a chance alignment of smaller structures masquerading as a single entity. But with every new gamma-ray burst mapped, the pattern holds, whispering that this isn't a trick of perspective, it's a real, physical anomaly. What makes the Hercules Corona Borealis Great Wall so unnerving isn't just its size. It's the quiet way it exposes how much we still don't understand about the universe's architecture. Like an explorer finding a city where maps showed only wilderness, astronomers are left grappling with a simple, humbling question. If this exists, what else might be out there, lurking just beyond the edge of our models? Perhaps the most thrilling possibility is that this isn't an exception but a signpost pointing to an even grander cosmic pattern, one we're only beginning to trace. In the vast echo of the cosmic microwave background, the afterglow of the Big Bang itself, there's a chilling anomaly that refuses to fit neatly into our understanding of the universe. Known as the cold spot, this mysterious region in the constellation Eridanus blazes a full 70 microkelvin colder than its surroundings, a discrepancy far too large to dismiss as random noise. At first glance, it might seem like a minor blip in the data, but when scientists traced its origin, they uncovered something even stranger. A sprawling, nearly empty region of space dubbed the Eridanus supervoid, stretching an astonishing 1 billion light-years across. The problem: such a void shouldn't exist, at least not according to our standard models of cosmic structure. The connection between the cold spot and the supervoid hinges on a phenomenon called the integrated Sachs-Wolf effect. As light from the CMB travels through the universe, it gains or loses energy depending on the gravitational pull of the structures it encounters. When photons pass through a dense cluster of galaxies, for example, they gain energy, appearing slightly hotter. Conversely, drifting through a vast void causes them to lose energy, cooling the light. But here's the catch: the Eridanus supervoid is so enormous and so empty that it should cool the CMB far more than what we observe. The math simply doesn't add up. It's like digging a hole in the ocean and expecting it to stay dry. The scales are too vast for the effect to be so subtle. This glaring inconsistency has led some cosmologists to propose radical alternatives. One theory suggests the cold spot might be the fingerprint of a collision with another universe, a bruise left by a cosmic sibling bumping against our own in the multiverse. The idea hinges on eternal inflation, a model where other universes bubble up beyond our observable horizon, each with its own physical laws. If one of these universes grazed ours in the distant past, the energy exchange could have left behind a cold imprint in the CMB, a ghostly handshake from a reality we'll never see. Skeptics, of course, point to more conventional explanations. Perhaps the supervoid isn't as empty as we think, or maybe the cold spot is a statistical fluke, an unlikely but not impossible clustering of random fluctuations. Others propose that the void's shape might be distorting our measurements, like looking through a funhouse mirror that warps the true scale of what's inside. But even these arguments struggle to fully account for the anomaly's persistence across multiple datasets, from Planck satellite observations to ground-based telescopes. What makes the Eridanus supervoid so compelling isn't just the scientific debate, it's the way it forces us to confront the limits of our knowledge. If it's truly a window into the multiverse, it would be the first tangible evidence of realities beyond our own. If not, it's still a cosmic puzzle begging for a solution, a reminder that even the oldest light in the universe still holds secrets we've only begun to unravel. Whether it's a flaw in our models or a glimpse of something far grander, one thing's certain: the cold spot refuses to be ignored. Long after sunset or just before dawn, if you find yourself under a particularly dark sky, you might notice something hauntingly beautiful, a faint pyramid-shaped glow stretching upward from the horizon, following the path of the zodiac constellations. This is the zodiacal light, a celestial phenomenon as enigmatic as it is delicate, often mistaken for the first blush of twilight or even distant city lights. But this eerie radiance doesn't come from Earth. It's sunlight reflecting off billions upon billions of dust grains scattered across the inner solar system, a shimmering veil that's puzzled astronomers for centuries. At first glance, the explanation seems straightforward. Asteroids colliding and comets shedding material should leave behind trails of dust which then drift inward toward the sun. But when scientists measured the zodiacal light's intensity and distribution, the numbers didn't add up. The dust is far too evenly spread, too smoothly dispersed, as if someone took a cosmic salt shaker and sprinkled it with perfect symmetry along the plane of the solar system. Even more perplexing, the dust grains are smaller and more abundant than most collision models predict, some no larger than smoke particles, yet collectively massive enough to catch sunlight across millions of miles. One theory suggests a hidden population of micrometeoroids, ground down over eons by countless impacts in the asteroid belt, could be the culprit. Others point to cometary debris, arguing that icy visitors like Halley or Encke might be shedding more dust than we realize as they loop around the sun. But the real mystery lies in the dust's persistence. Solar wind and radiation pressure should have blown these tiny particles out of the inner solar system long ago, leaving the zodiacal light to fade into oblivion. The fact that it hasn't implies a constant replenishment, a cosmic conveyor belt we're only beginning to map. Then there's the odd tilt. The zodiacal dust cloud doesn't align perfectly with the solar system's orbital plane. It's slightly warped, as if tugged by some unseen force. Some researchers speculate gravitational nudges from Jupiter or even interstellar gas could be skewing the dust's distribution. Others wonder if passing stars, long since moved on, left behind gravitational fingerprints that still shape the cloud today. What makes the zodiacal light so captivating isn't just its origin, it's what it reveals about our cosmic neighborhood. This isn't just dust, it's a fossil record of every asteroid collision, every cometary passage, every unseen ripple in the solar system's gravitational fabric. And as new telescopes peer deeper into its glow, they might find clues to even grander questions, like how planetary systems evolve or where Earth's own water and organic materials first came from. So next time you're under a dark sky, look for that ghostly pyramid of light. It's more than just a pretty glow, it's a whisper from the dust that built the planets, a reminder that even the emptiest corners of space are anything but empty. We know the universe is brimming with matter, but here's the twist. We can only find about half of what should be there. Not dark matter, not exotic particles, but ordinary baryonic matter, the protons, neutrons, and electrons that make up stars, planets, and even us. This is the missing baryon problem, a cosmic accounting error where the universe's ledger shows a staggering deficit. Based on precise measurements of the cosmic microwave background and primordial element abundances, scientists calculated that baryonic matter should account for roughly 5% of the universe's total mass energy. Yet when they tally up all the visible galaxies, gas clouds, and even wandering planets, nearly half of it's unaccounted for. Where did it go? One leading suspect is the WIM, the warm hot intergalactic medium, a vast web of diffuse gas threading the cosmos at temperatures between 100,000 and 10 million degrees. Unlike cold hydrogen clouds or blazing stars, the WIM is nearly invisible, emitting faint X-rays rather than visible light. Think of it as the universe's background hum, a whisper of ionized oxygen and nitrogen lurking in the spaces between galaxies. Detecting it is like trying to spot a single lit match in a foggy forest, possible, but only with the right tools. Recent breakthroughs using the Chandra X-ray Observatory and other instruments have begun spotting pockets of this elusive material. By observing how the WIM absorbs light from distant quasars like cosmic silhouettes against a backlight, astronomers have confirmed that at least some of the missing matter is hiding in these scorching filaments. But the WIM might not be the whole story. Another theory points to cosmic filaments, the sprawling highways of gas and dark matter connecting galaxy clusters. Simulations suggest these tendrils should be brimming with baryons, but their density is so low that traditional telescopes miss them. Enter the Sunyaev-Zeldovich effect, a subtle distortion in the cosmic microwave background caused by hot gas scattering photons. By mapping these distortions, observatories like the Atacama Cosmology Telescope have traced faint fingerprints of baryons in the filamentary web. It's like sensing the presence of a hidden river by the way it bends the wind. Then there's the possibility that some baryons are hiding in plain sight, just in forms we don't recognize. Ultra-diffuse galaxies, for example, are so sparse they're nearly transparent, while rogue planets and brown dwarfs drifting between stars could add up to significant mass without emitting much light. Even more intriguing, could some baryons be locked in primordial black holes, relics of the early universe too small to detect directly? What makes this mystery so compelling isn't just the hunt, it's what it reveals about our blind spots. For all our telescopes and supercomputers, the universe still keeps secrets in the spaces we least expect. Every unaccounted proton is a reminder that the cosmos is richer, stranger, and more inventive than our models predict. Whether it's the WIM, filaments, or something entirely unexpected, solving the missing baryon problem won't just balance the books, it'll rewrite our map of the unseen universe. At Saturn's North Pole, hidden beneath layers of swirling clouds, one of the solar system's most mesmerizing mysteries churns in near-perfect silence, a hexagon. Not a blurry approximation or a fleeting arrangement of storms, but a geometrically precise, six-sided jet stream large enough to swallow 4 Earths whole. First spotted by Voyager in the 1980s and later studied in stunning detail by Cassini, this colossal structure has endured for decades, possibly centuries, its razor-sharp edges defying the chaos of planetary atmospheres. Hurricanes on Earth last weeks. Jupiter's Great Red Spot has simmered for centuries, but neither compares to the Saturn hexagon, a storm sculpted into a polygon so flawless it looks engineered. The numbers alone are staggering. Each side stretches nearly 8,600 miles, with winds screaming at 320 miles per hour faster than a Category 5 hurricane. Yet despite this violence, the hexagon's shape remains eerily stable, rotating in sync with Saturn's deep interior every 10 hours and 39 minutes like a cosmic gear. What makes it even stranger is how isolated it is. While the rest of Saturn's atmosphere churns with turbulent bands and sporadic storms, the hexagon stands apart, a self-contained weather system locked in geometric rigidity. So why 6 sides laboratory experiments offer a clue. When scientists spin fluids at different speeds in a circular tank, polygons, including hexagons, can emerge at the boundary between fast-moving inner fluid and slower outer layers. On Saturn, this might translate to deep atmospheric currents interacting with the planet's own rotation, sculpting the jet stream into a polygon. But here's the catch: no simulation perfectly replicates the hexagon's sharp angles or longevity. Earth's oceans and atmospheres create transient eddies, but nothing this precise or persistent. Some researchers speculate that Saturn's lack of a solid surface plays a role, allowing the storm to anchor itself to deeper, unseen layers of flowing metallic hydrogen. Others propose that standing waves like vibrations frozen in the atmosphere could reinforce the hexagon's shape over time. Then there's the question of depth. Cassini's infrared eyes revealed that the hexagon plunges at least 60 miles down into Saturn's atmosphere, far deeper than most weather systems. This vertical structure might act like a planetary gyroscope, stabilizing the storm against disruptions. But even this explanation feels incomplete. Why doesn't the hexagon degrade or wobble like every other known atmospheric phenomenon? Why hasn't it sprouted additional sides or collapsed into a simpler shape? Perhaps the most haunting possibility is that we're seeing something fundamentally alien, a behavior of fluids and gases that only manifests under Saturn's extreme conditions, crushing pressures, blistering winds, and a composition dominated by hydrogen and helium. If true, the hexagon isn't just a curiosity, it's a window into physics we haven't yet imagined. A reminder that even in our own solar system, the rules can bend in ways we're only beginning to glimpse. One thing's certain: until another probe ventures into Saturn's amber skies, the hexagon will keep its secrets. It's a celestial monument to the universe's knack for turning turbulence into art, a shape that shouldn't exist yet does with quiet, relentless perfection. At the heart of our Milky Way, where stars crowd so thickly they blur into a golden haze, telescopes have picked up something that shouldn't be there: an eerie excess of gamma rays crackling with energy but with no obvious source. This is the galactic center excess, a mysterious glow first detected by NASA's Fermi Gamma Ray Space Telescope in 2009, radiating from the region around Sagittarius, a star, the supermassive black hole anchoring our galaxy. The signal defies easy explanation, pulsing with more high-energy light than known astrophysical objects can account for, as if the universe left a cosmic flashlight on deep in the galactic basement and forgot to turn it off. Initial excitement centered on dark matter as the culprit. Theoretical models suggested that weakly interacting massive particles, or WIMP hypothetical dark matter particles, could annihilate one another when they collide, releasing bursts of gamma radiation. The galactic center, with its immense gravitational pull, would naturally concentrate dark matter, making it the perfect hunting ground for such signals. The excess's energy profile even seemed to match predictions for certain WIMP models, sparking hope that we might finally have tangible evidence of the universe's hidden scaffolding. But the story quickly grew complicated. As observations sharpened, alternative explanations emerged, chief among them a vast population of millisecond pulsars. These ultra-dense neutron stars, spinning hundreds of times per second, emit gamma rays as their powerful magnetic fields whip particles to near light speeds. Too faint to spot individually at such distances, they could collectively mimic a smooth, glowing excess. Supporting this idea, researchers began identifying point-like gamma-ray sources in the region, each potentially a hidden pulsar. Yet skepticism lingered. The sheer number required thousands upon thousands seems implausible for a region that, by stellar demographics, shouldn't host so many. The debate hinges on subtle distinctions in the gamma-ray signal. dark matter annihilation should produce a smoother distribution of light, while pulsars would create a speckled pattern like fireflies in a fog. Current data teases both possibilities, with some analyses favoring one interpretation, others the opposite. Compounding the mystery, the excess isn't perfectly centered on Sagittarius, a star, but slightly offset, a detail neither dark matter nor pulsar models fully explain. Then there's the wild card, cosmic rays colliding with gas clouds. Protons accelerated by supernova or black hole activity could produce gamma rays when they slam into interstellar material, though calculations suggest this mechanism falls short of the observed excess. Unless, of course, our understanding of cosmic ray physics is incomplete, a recurring theme in modern astrophysics. What makes this enigma so captivating isn't just the science, it's the stakes. If dark matter, it's a landmark discovery, revealing the invisible hand shaping the cosmos. If pulsars, it's a testament to nature's ability to hide entire populations of extreme objects in plain sight. And if neither, well, that's when things get really interesting. The galactic center excess might be a signpost to physics beyond our current theories, a whisper from the universe that the galactic core holds deeper secrets than we've dared imagine. Until sharper telescopes or cleverer algorithms crack the case, it remains a glowing question mark at the heart of everything we know. Most galaxies look like scrambled eggs, messy spirals, lumpy ellipticals, cosmic blobs with stars flung every which way. But floating 600 million light-years away in the constellation Serpens, there's an exception so perfect it seems photoshopped, Hoag's object. This cosmic bullseye stares back at us with eerie precision, a dazzling blue ring of young, hot stars encircling a golden core of ancient suns, separated by a yawning gap of near-total darkness. No ragged spiral arms, no trailing debris, just a celestial donut suspended in the void. When astronomer Arthur Hoag stumbled upon it in 1950, he initially thought it was a planetary nebula, a dying star's final gasp. But the truth was far stranger, an entire galaxy playing by rules we're still trying to decode. The puzzle begins with that pristine ring. Typically, galaxy rings form through collisions. One galaxy plows through another, triggering waves of star formation that ripple outward like splashes in a pond. But Hoag's object shows no signs of violence, no twisted trails of dust, no warped cores hinting at a past catastrophe. It's as if the ring simply appeared, a celestial halo that sprang into existence without the usual cosmic demolition derby. Even more baffling, the gap. Most ringed galaxies have some stars or gas bridging the core and outer disk, but Hoag's object's dark channel is almost impossibly clean, like someone took an eraser to the space between. One theory suggests a secular instability, a slow-motion rearrangement where the galaxy's own gravity reshapes its structure over billions of years, funneling gas outward to form the ring while the core contracts. Another idea points to an ancient, long-vanished companion galaxy whose gravitational tug might have stirred the outer disk into forming stars in this precise configuration. Then there's the dark horse candidate, a phenomenon called accretion-driven star formation, where intergalactic gas trickles in from the cosmic web, igniting new stars in a perfect circle without any collision at all. But the weirdness doesn't stop there. Peering deeper, astronomers found another surprise, an even more distant ring galaxy lurking behind Hoag's object, visible through the gap like a cosmic nesting doll. This chance alignment hints that such structures might be more common than we thought, hidden in plain sight until our telescopes catch them at just the right angle. It's a sobering reminder, for every Hoag's object we spot, how many others are out there, their symmetry too edge-on or faint for us to recognize. What makes this galaxy so mesmerizing isn't just its beauty, it's the way it forces us to rethink what galaxies can be. Maybe rings don't always require chaos. Maybe there are quieter, more elegant paths to perfection in the universe. or perhaps Hoag's object is the exception that proves the rule, a cosmic fluke that stumbled into symmetry against all odds. Until we find more like it, this celestial enigma will keep spinning in the dark, a silent challenge to our understanding of how galaxies live, grow, and sometimes, against all expectations, carve themselves into art. On the morning of June 30th, 1908, a patch of remote Siberian wilderness became ground zero for one of the most violent cosmic events in recorded history. At 7:17 a.m. local time, eyewitnesses reported a fireball streaking across the sky brighter than the sun, moving at impossible speed before a cataclysmic explosion flattened an estimated 80 million trees across 830 square miles. The blast, later estimated at 10 to 15 megatons of TNT, sent shockwaves that shattered windows hundreds of miles away and lit up skies as far as London. Yet when expeditions finally reached the epicenter decades later, they found something baffling. No crater, no fragments, just a radial pattern of scorched, toppled trees pointing outward like spokes on a wheel. This was the Tunguska event, a cosmic mystery that spawned everything from sober scientific theories to wild speculation about the fabric of reality itself. The leading explanation points to an airburst, a comet or asteroid exploding in the atmosphere before hitting the ground. At 5 to 10 kilometers above the Taiga, the pressure and heat would have vaporized the object instantly, unleashing energy equivalent to 1,000 Hiroshima bombs without leaving a traditional impact scar. Supporting this, researchers found microscopic silicate and magnetite spheres in the soil, melted droplets that could be remnants of a stony meteorite. But here's the twist: no sizable fragments have ever been recovered, and scans of the area reveal no buried remnants. This suggests the intruder might have been a fragile comet, a loosely packed snowball of ice and dust that disintegrated completely in the blast. Yet competing theories refuse to fade. Some physicists have floated the idea of a microscopic black hole, a hypothetical primordial singularity left over from the Big Bang, passing through Earth like a bullet through tissue, exiting near the North Atlantic with no trace beyond the Tunguska devastation. Others suggest an antimatter meteorite annihilating itself in a flash of gamma rays upon contact with ordinary matter. Both ideas, while captivating, strain credibility. Black holes of that mass should still be detectable today, and the universe's scarcity of antimatter makes such an event astronomically improbable. Then there are the wild cards. Could it have been a natural hydrogen gas explosion, a pocket of subterranean methane igniting under rare atmospheric conditions? Unlikely given the fireball's observed trajectory. Or, as a handful of fringe researchers insist, might it have been the catastrophic failure of an alien spacecraft's propulsion system, a notion fueled by reports of odd geomagnetic disturbances in the region days before the event? What makes Tunguska endure isn't just the unanswered questions, it's the chilling reminder of our planet's vulnerability. Had the explosion occurred 4 hours later, Earth rotation would have placed St. Petersburg or Stockholm in the crosshairs, potentially claiming millions of lives. Today, NASA, a planetary defense coordination office, scans the skies for similar threats, but Tunguska's legacy lingers. A warning shot from the cosmos, a blast whose true nature might forever hover just beyond our grasp. Whether comet, black hole, or something stranger, one thing's certain: when the next one comes, we may not be so lucky. For nearly a century, astronomers have measured the universe's expansion rate, a number so fundamental it's called the Hubble constant, the yardstick by which we gauge the cosmos' growth. But lately, that yardstick has split in two. Depending on how you measure it, the universe seems to be expanding at different speeds, a discrepancy so stubborn it's been dubbed the Hubble tension, and it's rattling the foundations of modern cosmology. On one side, we have the early universe's echo, the cosmic microwave background, its faint afterglow revealing an expansion rate of about 67 kilometers per second per megaparsec. On the other, the glittering standard candles of nearby galaxies, Cepheid variables, and supernova insist the number is closer to 73. At first glance, the difference seems small, but in the precise world of astrophysics, it's a chasm. These numbers should agree. Instead, they're diverging with every new measurement, as if the cosmos itself can't decide how fast it's growing. Why does this gap matter? Imagine building a bridge where the blueprints disagree on the length by 5%. You might shrug until the first cars cross and the structure shudders under the strain. The Hubble constant isn't just a speed limit sign. It's woven into every calculation about the universe's age, composition, and fate. If we've misjudged it, entire chapters of cosmic history might need rewriting. The tension exposes a crack in our understanding of dark energy, dark matter, and even the Big Bang's aftermath. What if we've overlooked something fundamental, a force or particle that tweaks the universe's expansion like a hidden dial? One camp argues the discrepancy is a measurement fluke, an accumulation of tiny errors in how we track distant stars or interpret the CMB's subtle wrinkles. But as telescopes grow sharper and datasets balloon, the gap refuses to close. Others propose more radical fixes. Maybe dark energy isn't constant but evolving, growing stronger over time. Or perhaps there's an unknown, dark radiation component left over from the universe's first seconds, subtly altering the expansion's tempo, the wildest idea. That we're seeing fingerprints of a shadow universe, a parallel realm of particles interacting with ours only through gravity, warping space-time in ways we're just beginning to sense. The Hubble tension isn't just a technical debate, it's a crossroads. Either we're on the verge of discovering new physics, or we've underestimated the complexity of the tools we've relied on for decades. With next-generation observatories like the James Webb Space Telescope and the Vera Rubin Observatory joining the hunt, the answer might be closer than we think. Whatever the solution, one thing's certain: the universe is expanding, and so is the mystery of how fast. For decades, dark matter has been the reigning explanation for why galaxies rotate too fast, why clusters bend light more than visible mass can explain, and how the cosmic web took shape. The idea is simple. An invisible, slow-moving particle permeates the cosmos, its gravity sculpting the universe while remaining undetectable except through its pull. But what if we've been chasing a ghost? A small but vocal group of physicists argues there's another possibility, one that doesn't require inventing a new type of matter. Instead, they propose tweaking the laws of gravity themselves. This isn't just academic squabbling, it's a clash of paradigms, with each side marshalling evidence from galactic scales to the earliest moments of the Big Bang. Take modified Newtonian dynamics, or MUND, the most prominent challenger to dark matter. Proposed in the 1980s by physicist Mordechai Milgrom, MUND suggests that gravity behaves differently at extremely low accelerations like those found in the outskirts of galaxies. Newton's laws work fine for planets orbiting the Sun or apples falling to Earth, but in regions where gravity's pull is vanishingly weak, Milgrom argued, the force strengthens subtly. This tweak could explain why stars in galactic fringes orbit faster than predicted without invoking unseen matter. Early successes were striking. MUND reproduced galaxy rotation curves with uncanny precision, matching observations better than some dark matter models. But the devil's in the details. While MUND excels at describing individual galaxies, it stumbles when faced with larger structures. Galaxy clusters, for instance, contain so much hot gas and dark mass that even modified gravity can't fully account for their observed behavior without adding some form of invisible matter, essentially reinventing the problem it sought to solve. Then there's the bullet cluster, a cosmic collision where gravitational lensing reveals mass concentrated where no visible matter exists, a smoking gun for dark matter's presence. MUND proponents have devised workarounds like positing unseen neutrino-like particles, but these patches stretch the theory's elegance. Meanwhile, the hunt for dark matter particles grows ever more sophisticated. Underground labs like LUX Zeppelin and Xenon 1T scour for WIMP, while action detectors tune into the faintest whispers of quantum fields. Yet after decades and billions of dollars, these experiments have turned up empty-handed. The null results aren't necessarily fatal. WIMP might simply be rarer or more elusive than predicted, but they've fueled skepticism. Some theorists argue we're trapped in a paradigm, pouring resources into a particle that might not exist while sidelining alternatives. The truth might lie in synthesis. Certain hybrid models, like emergent gravity, attempt to bridge the gap, suggesting dark matter is an illusion caused by spacetime's microstructure. Others explore dark fluid theories, where dark matter and dark energy unite as a single exotic substance. But until a definitive detection or a revolutionary observation tilts the scales, the debate rages on. What makes this conflict so compelling is its stakes. Dark matter's triumph would confirm a universe mostly invisible, governed by particles beyond our standard model. Modified gravity's victory would rewrite physics textbooks, proving Einstein's framework incomplete. For now, the cosmos keeps its secrets, dangling clues just out of reach. Whether the answer lies in unseen matter or uncharted laws, one thing's clear: our understanding of gravity is anything but settled. The idea that fast radio bursts could be more than just cosmic fireworks, that they might be deliberate signals from an advanced civilization, sends shivers down the spine of anyone who stared up at the stars and wondered. It's a tantalizing thought, especially when you consider the raw power packed into those millisecond flashes. Some FRBs emit more energy in 1,000th of a second than our sun does in 3 days. Could something or someone be harnessing that kind of power? Take the game-changing discovery in 2020, when astronomers traced an FRB-like burst to a magnetar in our own galaxy, SGR 1935 plus 2154. Suddenly, we had proof that at least some FRBs could be produced by these ultramagnetic stellar corpses. But here's the twist: this galactic FRB was orders of magnitude weaker than its extragalactic cousins. It's like comparing a firecracker to a nuclear explosion, similar mechanics but vastly different scales. That leaves a glaring question. If magnetars can only explain the faint end of the FRB spectrum, what's cranking out the real monsters? This is where the technosignature debate heats up. Researchers like Harvard's Avi Loeb have speculated that the most energetic, non-repeating FRBs could be artificial, perhaps the byproduct of alien propulsion systems. Imagine a civilization harnessing the power of a star to accelerate light sails to relativistic speeds. The energy required would be staggering, and the leakage from such a process might look an awful lot like an FRB to distant observers. Then there's the beacon hypothesis. What if advanced societies are intentionally broadcasting these bursts as cosmic lighthouses, designed to stand out against the background radio noise of the universe? The narrowband nature of some FRBs, their millisecond precision, even the curious frequency drift observed in a few, all could be engineered features rather than natural phenomena. But before we jump to conclusions, there's a crucial detail to unpack. The fact that we've now linked one FRB to a known astrophysical source, the Milky Way's magnetar, changes the playing field. It proves nature can produce these signals without any alien intervention, at least in some cases. Occam's razor suggests most FRBs likely have similar origins: magnetars, neutron star collisions, or other extreme but natural events we've yet to characterize fully. Yet the outliers, the ones that don't fit the magnetar mold, keep the door cracked open for more exotic explanations. What makes this debate so fascinating isn't just the science, it's the philosophical tightrope we walk. On one hand, dismissing the possibility of technosignatures outright risks blinding us to genuine discoveries. History shows that new phenomena often defy initial expectations. Pulsars, when first detected in 1967, were briefly nicknamed LGM-1, Little Green Men, because their perfectly timed pulses seem too artificial to be natural. On the other hand, overinterpreting anomalies as evidence of aliens can lead science astray, wasting resources on dead-end searches, the way forward. Rigorous skepticism paired with open-minded curiosity. Projects like Breakthrough Listen now include FRBs in their search for technosignatures, analyzing bursts for patterns or modulation that might hint at intelligence. Meanwhile, radio telescopes like CHIME and FAST are compiling vast FRB catalogs, hunting for statistical oddities, repeaters with unnatural periodicity, or bursts clustered in ways that defy random distribution. Ultimately, whether FRBs are cosmic accidents or cosmic hellos, they've already done something remarkable. They've forced us to confront how little we know about the universe's most energetic phenomena. And in that uncertainty lies the thrill of discovery, the chance that one day, amidst the static and the noise, we might stumble upon a signal that's anything but random. Picture yourself standing in a hall of mirrors, except instead of reflections, each mirror shows an entirely different universe with its own laws of physics, its own constants, even its own version of you. This isn't just science fiction, it's one interpretation of the multiverse, a hypothesis that our cosmos might be just one bubble in an infinite froth of realities. And some researchers believe the first hard evidence for this mind-bending idea might be hiding in the oldest light we can see, the cosmic microwave background, specifically in that baffling alignment known as the axis of evil. At first glance, linking a slight temperature asymmetry in the CMB to alternate universes seems like a stretch, but the reasoning hinges on cosmology's deepest mysteries. If our universe collided with another during its inflationary infancy, a period of breakneck expansion just after the Big Bang, the energy from that impact could have left a bruise in the CMB, a subtle directional preference that manifests as the axis of evil. Think of it like a fingerprint on a window, a smear left by something passing by outside our observable realm. Supporters of this idea point to simulations showing how bubble universes in a larger multiverse would inevitably jostle one another, creating signatures in their respective backgrounds. But critics fire back with a simple question. If this is evidence of a multiverse, why isn't the signal stronger? The axis of evil's deviation from uniformity is subtle, a fluctuation measured in microkelvins. Shouldn't a head-on collision with another reality leave a more dramatic scar? Skeptics also highlight the peril of confirmation bias, how easy it is to interpret any anomaly as proof of a pet theory when the truth might be far duller. The CMB is notoriously difficult to measure cleanly, with foreground interference from galactic dust and the Doppler effect of our solar system's motion both potentially skewing results. Even the Planck satellite's painstaking maps, which confirmed the anomaly, couldn't rule out systematic errors entirely. Then there's the philosophical objection. If the multiverse is untestable by definition, with other universes forever beyond our observational reach, does invoking it to explain cosmic quirks count as science or metaphysics? Some physicists argue it's no different than attributing anomalies to gods or magic, a retreat from the hard work of finding explanations within known physics. Others counter that while the multiverse hypothesis is speculative, it's grounded in quantum field theory and inflationary cosmology, frameworks with robust experimental support. The real issue isn't whether the multiverse exists, but whether we can ever gather definitive proof. Amid the debate, one thing is certain: the axis of evil refuses to vanish under scrutiny. Whether it's a window into the multiverse, a statistical fluke, or a signpost to new physics, it underscores how much we still don't understand about the universe's first moments. And that's the real value of anomalies. They keep us questioning, pushing the boundaries of what we think we know. The cosmos might not be playing fair, but that's what makes the game worth watching. From the Great Attractor's mysterious pull to the fleeting whispers of fast radio bursts, These 25 cosmic enigmas aren't just curiosities, they're the frontiers of human understanding. Each one represents a crack in the facade of our knowledge, an invitation to dig deeper, to question everything. Think about dark matter, that invisible scaffolding holding galaxies together, or dark energy, the phantom force ripping the universe apart. These aren't just gaps in our maps. They're chasms forcing us to rewrite the rules of physics itself. Even the humble moon, our closest neighbor, guards secrets about magnetic fields that defy expectations, proving there's wonder lurking in the most familiar places. Take something as seemingly mundane as the zodiacal light, that faint glow along the ecliptic. It's more than just sunlight bouncing off dust. It's a ledger of cosmic history, a record of every asteroid collision and comet's passage. Or consider Saturn's hexagon, a storm so geometrically perfect it looks engineered. These phenomena don't just puzzle us, they push us to build better telescopes, design sharper simulations, and dream up wilder theories. The Hubble tension, the great filter, the missing baryons, they're not dead ends. They're signposts pointing toward the next revolution in science, and that's the beauty of it. Every mystery solved unveils 10 more, each more tantalizing than the last. The universe isn't just stranger than we imagine, it's stranger than we can imagine. So stay curious, keep looking up, because somewhere out there, hidden in the static of a radio signal or the flicker of a distant star, might be the clue that changes everything. The cosmos isn't done surprising us yet, and who knows, the next big discovery could be yours.